Hi Mendez mathematicians, welcome to lesson 6.2, our second lesson in Unit 6, Intro to Quadratic Functions. Our lesson is called How Does It Change? We're going to build on what you did yesterday with looking at a word problem of a fence around a specific area, and now we're going to be looking at a patterns of squares and dots to look at how they're growing. And so your first learning target today is to be able to describe how a pattern is growing. Next, that you can tell whether a pattern is growing linearly, exponentially, or quadratically. And last, that you know an expression with a squared term is called quadratic. First, for our warm-up, please take a look at this figure and see how each of the four expressions underneath the figure represents the number of small squares in this figure. You may have answered that in expression A, we have 6 times 8 minus 2 times 3. The 6 times 8 is representing 6 rows with 8 small squares. So these 6 rows, these 8 small squares in each row, that would be a rectangle of 48 squares, 6 times 8. But we're subtracting this section up in the top right corner because that's missing. So we're subtracting off 2 rows of 3. For expression B, this time we also see the 8 for 8 squares in the row, but it only counts these 4 rows here at the bottom that have all 8 of those squares. So 4 times 8, and now plus 2 times 5 to add on these 2 rows of 5 above. Expression C, 8 plus 8 plus 8 plus 8 plus 5 is also actually really similar to expression B because we have these 8s being added up, 4 of them. This is like saying instead of 4 rows of 8, this is counting them up separately. So 8 for this row plus 8 plus 8 plus 8. And then after that, we're adding plus 5 for the next row and plus 5 for the very top row. So expression C is counting 1 row at a time, starting from the bottom. So adding up the number of small boxes in each of those rows. The last one, expression D, this would be if you're looking at it in terms of columns. So here we have 5 columns of 6 small squares. So this rectangle over here is 5 columns, so counting 5 this way, by 6 small squares. To get this additional piece to the right, we're also going to add plus 3 columns of 4 small squares. So you can see that all 4 of these expressions are equivalent. They all give us the number of squares in this figure. In today's lesson, we're going to be wanting to look for different ways we can visualize how patterns are changing, and so it'll be helpful to keep in mind this idea of looking at rows, looking at columns, looking at what maybe has been added or subtracted to different shapes. Let's go ahead and build onto that, looking at these two patterns, pattern 1 and pattern 2. Look at these two patterns of dots and answer first, how do you see the number of dots changing? And next, how would you find the number of dots in the 5th step in each pattern? For pattern 1, there's lots of different ways to see how this is growing. You may be visualizing it as having this triangle that's then having pieces added. You may be seeing it as there's this dot that's on the left that's always hanging out there, and then things are changing next to it. One way that you can be looking at this is that each step has 2 rows of dots. So in step 1, we have these 2 rows of dots. Step 2, we have these 2 rows of dots. Step 3, we have these 2 rows of dots, where each of those rows has the same number of dots as the step number, and then also plus this 1 extra dot on that bottom left. That means that for step 5, there would be 2 rows of 5 dots plus 1 additional row. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the 11th dot on the bottom left. For pattern 2, step 0 doesn't have any dots, and then step 1 has 1. Step 2 and step 3 are continuing to grow, and these are forming squares. So in pattern 2, each step has as many rows and columns of dots as the step number. So for step 0, 0 rows of 0 columns, there's no dots. Step 1, 1 row of 1 column, we have 1 dot. Step 2, we have 2 rows and 2 columns. Step 3, we have 3 rows and 3 columns. So that means that step 5 would be a 5 by 5 array, so 5 columns and 5 rows. Okay, I'm not going to draw all of those dots, but you could if you wanted to. It's going to be 5 this way and 5 that way. All right, next we're going to complete this table with the number of dots in each pattern. And I'll get us started with which ones we already have here. So pattern 1, in step 0, we have 1 dot already. Whereas pattern 2, step 0 has 0 dots. In pattern 1, step 1 goes up to 3 dots. So we have these 2 new ones added. And step 2 has 5 dots. And step 3 has 7 dots. So it's going up by 2 each time. So step 4, we'd be able to say, okay, that should have 9. Step 5 should have 11 squares. But if we have to jump all the way to what step 10 would look like, or even just in general, what would the nth step look like for a particular step number n, we want to kind of think about what the structure of this is. So like we had on the previous slide, it said that there were these 2 rows. Each of them was going to have as many dots as the pattern number. So 2n and then plus 1. So for instance, for step 10, there would be 2 rows of 10. So that's 20 plus 1. So 21. And in general, if we have any value of n for the step number, there would be 2n plus 1 dots for 2 rows, and then plus that 1 extra that's always hanging out in the bottom left corner. For pattern 2, we have step 0 has 0 dots, step 1 has 1 dot, step 2, because we had these 2 rows and 2 columns, we had 2 times 2 or 4 dots. Step 3, we have these 3 rows and 3 columns, giving us a total of 9 dots. Take a moment now to see how many dots there would be in step 4, 5, and step 10, and also see if you can come up with an expression for the number of dots in pattern 2. Right, without having to draw out all of the dots, we know that for each of these cases, the step number is going to tell us how many rows and how many columns. So for step 4, there's going to be 4 times 4 dots, or 16. And for step 5, we would have 5 dots, 5 rows and 5 columns for a total of 25 dots. And last, for the numbers at least, last we have, if we had step 10, that would be 10 rows by 10 columns, so 100. So what's happening here is whatever the step number is, that's going to tell us how many rows and columns. So that's going to tell us kind of the length and width of this rectangle. Because it's the same for all of the sides, that means it's a square. And we can express this as n squared. So the step number times itself, because that's the number of rows and the number of columns. Now we're going to compare the graphs of the two patterns. Why do these graphs look the way they do? Going from this first pattern, we can see that as we had first 1 dot, and then 3 dots, and then 5 dots, and then 7, each time it's growing by 2 dots. So each time we have this slope where it's going up 2 every time it goes over 1. So every time we go from one step number to the next, it's going up 2 for every time we go one step number to the right. For pattern 2 though, it's not growing that way. We would be adding 1, and then adding 3, and then from 4 to 9 adding 5. Okay, so even though there seems to be a pattern in that, we're not growing by the same amount each time. There's not going to be a slope or the same number that's being added to y every time that x increases. So because of that, our pattern 2, when we graph the points for how many dots are in each step number of that pattern, it's going to curve, and that's going upwards. It's like it's growing steeper than it would have if it just started on this linear function. It's starting to grow faster and faster. So already we've seen linear functions like the one in pattern 1, and we've seen patterns that grow in a curve. Last unit we saw our exponential functions where we had a number to the power of our variable. Take a look at what's different here in pattern 2, and how do you see the change in the tables and in the graphs? Pattern 1 is linear, and we can see in the table that for every from one point to the next, our change in y, or the value here for the number of dots, over the change in x, so the change in step number, is always going to be 2. It's always growing by 2 as n increases. Whereas for the one on the right in the table, or the lower one for the pattern and the graph, pattern 2, this is a quadratic. This is growing by having a term, in this case n, and then squaring it. So our step number for each of the steps in the pattern is going to be multiplied by itself or squared to get the expression to represent that number of dots in pattern 2. Let's practice by looking at another pattern. This one's a pattern of squares. What do you notice, and what do you wonder? All right, we've looked at these 3 steps in a pattern and wrote down what you noticed and what you wondered. You may have noticed that in step 1 there are 3, while step 2 has 6 dots and step 3 has 11 dots. Visually, you may have noticed that there's kind of this middle section that's getting bigger as we go from one step to the next. You can keep that in mind as you are answering the next question. Number 1, is the number of small squares growing linearly? Explain how you know. one way we would check if something is growing linearly is, does it have the same rate of change? So from one step to the next, is it adding the same number of squares? Step 1 we have 3, but step 2 we already have 6. And by step 3, there's already 11. So that's not growing by the same amount. So that's not going to be linear. Completing the table here, we have step 1 has one small square and then 2 on either side. Step 2 has a square made up of 2 rows and 2 columns, and then still just has these little extra squares on the side. And then step 3, the middle section is a 3 by 3 square with just the 2 extra blocks on the sides. So whatever the number of squares is, we're going to have this middle section that has the number of rows and columns are coming from the number of the step we're on. And then these 2 extra ones that are just always going to be there on the left side and on the right side. So step 1 had 3 squares. Step 2 has these 4 in the middle plus the 2 on the outside. So there are 6. Step 3 has this square of 3 times 3, so these 9 in the middle, and then plus the ones on the other side, on either side, so 9 plus 2 is 11. If this were step 4, we'd have 4 by 4 would give us 16 in the middle, plus each one on the left and right, we'd have 16 plus 2 is 18. For the 5th step, the center square would have 5 by 5, or 25 squares, plus those 2 extra ones on the left and right, so we have 27. And if we were to jump to whatever larger step number, such as step 10, that's going to tell us the number of rows and columns for this middle section. So 100, and then we always have these extra 2 dots on the left and right. So 102 for 10 dots, or for 10 steps. For 12, for step 12, we have 12 times 12, so 144 tiny squares in the center section, and then a square on each, the left side and the right side, so 144 plus 2 is 146. And then, once again, regardless of what the step number is, then our step number is going to tell us the number of rows and columns, and then we're adding 1 on either side. So either n times n plus 2 or n squared plus 2. So this is not growing exponentially. We saw it wasn't growing linearly because it wasn't adding by the same amount from one step to the next. It's not growing exponentially either because there's not a common factor that it's multiplying by from one step to the next. From step 1 to 2, it goes from 3 to 6, so it doubles. But then from the next step, from 6 to 11, 11 to 18, 18 to 27, it's not growing by multiplying by 2, it's not doubling. So there's going to be different numbers that it's multiplying by over those intervals. Whereas for an exponential function, the values increase by equal factors, or multiplying by the same thing over equal intervals. So this one is not linear or exponential. Just like pattern 2 from our previous activity, this one is quadratic. And we're calling it quadratic. It has this expression where we have n squared plus 2. So the fact that there's that squared term indicates to us that this is quadratic. All right, so our definition then of a quadratic expression A quadratic expression in x is one that is equivalent to an expression of the form ax squared plus bx plus c, where a, b, and c are constants and a is not equal to 0. So what does that mean? So we had earlier, we had something that was growing where we had n squared plus 2. So in this case, it would be a quadratic expression in n, where it was 1n squared plus 0n plus 2. If we have an expression like x plus 5, that's not quadratic because we need to have an x squared term. We need to have this ax squared, where a can't be equal to 0. So a quadratic expression, we have some number of x squareds, or whatever our variable is, squared, and then we may or may not have additional additional terms that are just the first power of that variable and the 0th power, or not having any, so the constant term here. All right, so once again, our quadratic expression in x, that just means whatever the variable is that we're using, we're going to have a coefficient times that variable squared, and then possibly plus bx, or plus a certain number of the variable to the first power, plus, and then a certain constant number. Remember that b and c also could be negative values, so this might look different, but we have the general structure ax squared plus bx plus c. All right, revisiting our learning targets, describing how the pattern is growing. We described that in words for a few different patterns of dots and squares. For telling whether a pattern is growing linearly, exponentially, or quadratically, remember that we're looking at, for linear, is it growing by adding the same amount over equal intervals? Exponentially, is it multiplying by the same amount over equal intervals? Or quadratic, where we haven't exactly explored how to describe precisely what the rule is, but we know that something's going on with a squared, with an exponent of 2. So an expression with a squared term is called quadratic. All right, don't forget to do your cool down by midnight tonight, and have a wonderful rest of your day.